Let's consider an example to underscore the value in transporting power at high voltage across long distances. So we're going to consider the following problem. To provide power to a small city, a power plant generates 40 megawatts of AC electricity. The power plant is 50 miles away from a city, or 50 kilometers away from a city, and this is a typical distance. And the 100 kilometer wire used in the transmission, we have to go to the city and back again, has a resistance of 7 ohms. So the entire line that goes from the power plant to the city and back again has a total resistance of 7 ohms, which is really quite small considering how long that piece of wire is, but these are very thick wires that are used. Here are basically the questions. To provide 40 megawatts of power at the generator voltage of 25,000 volts, what current is required? If we were to provide 40 megawatts of power at 25,000 volts across the countryside, what is the current required? And then B, what is the power dissipated in the resistance of the transmission line for this current? Alternatively, we could transport it at 500,000 volts. So part C says, to provide 40 megawatts of power at 500,000 volts, what current is required? And then D, what is the power dissipated in the resistance of the transmission line for this higher voltage? So let's treat the city as one big load, and the wires that transmit the power to it as a load. So the wires that transmit the power to the load, to the city, and the city itself as one large load that is being powered by this power plant. And we're going to find the current required to provide the 40 megawatts of power for these two different scenarios, one for 25,000 volt transmission and one for 500,000 volt transmission. The voltages are RMS values, so 25,000 volts is the RMS voltage for the power plant output, and 500,000 volts is the RMS voltage for the transmission lines. To summarize the question then, what is the difference between transporting the 40 megawatts of power over a 25,000 volt transmission line and a 500,000 volt transmission line? Do we gain efficiency, and if so, what is it? So to provide 40 megawatts at the generator voltage of 25,000 volts, in other words, to transport that 25,000 volts across the countryside, IRMS is going to be the power divided by the voltage. Remember that we learned that power is equal to IRMS times VRMS, and therefore I is going to be the power P divided by V, and that's what we see here. IRMS is going to be the power P divided by the RMS voltage, and if we take those two numbers and divide them, we get 1600 amps. That's a lot of current. 1600 amps is a lot of current. The real question is, what does that do in terms of the dissipated power? How much heat does that provide in the lines because of that loss? The resistance is only 7 ohms. It's fairly small, but the current is high. The power dissipated in those wires is equal to IRMS squared times the resistance R, which is 1600 squared times 7, which ends up with a result of 18 megawatts. 18 million watts of power is lost simply in the lines themselves delivering power to the city. That's a huge loss. That's nearly half of the 40 megawatts that we produced. So in order to transport 40 megawatts over a distance of 50 kilometers, it seems unwise to use a voltage of 25,000 volts. It's not high enough because it doesn't lower the current enough. The lower the current, the lower the dissipated power. And in fact, we gain because the power dissipated goes as I squared. Earlier we saw a step-down transformer, or a step-up transformer that went from, well, I can't remember the numbers, but we had an increase in voltage of 20. We stepped up the voltage by 20 and we stepped down the current by 20, but then we stepped down the power dissipated by 20 squared, or 400. So if we can step up the voltage by a factor of 20, which means stepping down the current by a factor of 20, we reduce the power dissipated by a factor of 40, or 400. So let's see what it means in the case of 500,000, or in the case of 25, in the case of 25,000, we found out that the power loss was 18 megawatts. But now let's consider the case of 500,000 volts. The RMS current is going to be the power divided by the RMS voltage, which in this case gives us 80 amps. If we transport the power at 500,000 volts, the current in the lines is 80 amps. And that's actually a rather small amount to supply to an entire city, but remember, it's being transported at 500,000 volts. We're going to step it down to a reasonable value before it's used by the consumers in that city, at which point the voltage is going to drop considerably, ultimately down to 120 volts, which is going to step the current up considerably as well. So let's calculate that power dissipated. This current is much smaller. When you take 80 squared and multiply it by 7 ohms to find the power loss dissipated in the wires, we end up with 0.045 megawatts. That's only about 0.1% or 1/10% of the power generated, which is much more reasonable. We can never avoid the power loss, but we can certainly reduce it by kicking the voltage up using a transformer to very high values, transporting it across the countryside, and then stepping it back down. The intermediate step of transporting that power is made much more efficient by stepping up that voltage as high as we can. And 500,000 volts is fairly commonly used for transmission lines, especially over large distance.